Earth fault loop impedance, Z, is a critical concept in electrical engineering, particularly in ensuring the safety and reliability of low-voltage electrical installations. It refers to the total impedance of the electrical path that a fault current would take in the event of an earth fault, from the point of the fault back to the source of supply. Understanding and measuring earth fault loop impedance is essential for ensuring that protective devices, e.g., circuit breakers or fuses, operate correctly to disconnect the supply in a fault condition, preventing electric shock, fire, or equipment damage. Okay, here we will look at some of the key concepts associated with earth fault loop impedance. What is an earth fault? An earth fault occurs when a live conductor unintentionally comes into contact with an earthed conductive part. For example, a metal appliance casing or earth wire. This creates a low-resistance path for fault current to flow from the live conductor to earth and back to the supply transformer. Earth fault loop path. The fault current follows a specific loop, referred to the red dotted line in the diagram. From the supply transformer's live conductor, which is the brown wire at the top of the diagram, note the impedances Z and R1. Through the fault point, that is where the live brown conductor touches the earthed metal casing of the toaster. It then flows through the protective earth conductor, or CPC circuit protective conductor, which is the green wire containing the impedance R2. The fault current then flows back to the supply transformer via the earthing system. The impedance of this entire loop is called the earth fault loop impedance, ZS. Okay, now we will look at the formula and associated components of earth fault loop impedance, ZEE. External loop impedance, impedance of the supply network up to the installation, including the transformer and supply cables. R1, resistance of the phase conductor within the installation. R2, resistance of the protective earth conductor, CPC, within the installation. Formula, ZS equals ZE plus R1 plus R2. Why is ZS important? The main reason is safety. Low ZS ensures sufficient fault current flows to trip protective devices, for example circuit breakers or fuses, quickly in an earth fault, disconnecting the supply to prevent shock or fire. Another reason it's important is compliance with electrical standards, e.g., IEC 60364, BS 7671. Specify maximum ZS values to ensure protective devices operate within required disconnection times. For example, 0.4 seconds for final circuits in TN systems. Another reason it's important is reliability. High ZS can indicate poor connections, undersized conductors, or inadequate earthing, leading to unreliable protection. Now we will look at factors affecting ZS cable length. Longer cables increase R1 and R2, raising ZS. Cable size. Smaller cross-sectional areas increase resistance, raising ZS. Connections. Loose or corroded connections increase impedance. Earthing system. The type of earthing system, for example, TNS, TNCS, TT, affects ZE and the overall loop impedance. Typical maximum ZS values. Standards like BS 7671 provide tables of maximum ZS for different protective devices and circuit ratings. Example, for a 32, a Type B circuit breaker in a 230 volts TN system, the maximum ZS might be around 1.37 ohms to ensure disconnection within 0.4 seconds. Okay, now we will look at earthing systems and ZS, and it's very important to keep in mind the ZE is totally dependent on the DNO, and its value is out of the control of an electrical designer. Right. The earth fault loop impedance varies depending on the earthing system. For example, in a TNS, separate neutral and earth system, the earth is provided by a separate conductor from the supply transformer. This is typically low ZS due to a reliable metallic earth return path. In the case of a TNCS, combined neutral and earth system, the neutral and earth are combined in part of the system. For example, PME, protective multiple earthing. This system is characterized by low ZS, similar to TNS, but depends on the integrity of the neutral earth link. And finally, the TT, local earth electrode system. This installation has its own earth electrode, e.g., earth rod. It's characterized by higher ZS due to the resistance of the earth electrode, often requiring residual current devices, RCDs, for protection. And finally, to sum up, summary, earth fault loop impedance, ZS, is the total impedance of the path taken by fault current during an earth fault. It determines whether protective devices will operate quickly enough to ensure safety. Low ZS is critical for effective fault protection, and it depends on the earthing system, cable characteristics, and connection quality. Regular testing and adherence to standards ensure compliance and safety in electrical installations.